So there's no phase shift between them. We know that the current in the inductor is out of phase with the voltage by 90 degrees. So there it is at minus 90 degrees. It's out of phase by 90 degrees. We know the current IC is out of phase from the voltage by 90 degrees, but of course leading the voltage by 90 degrees such that it's there. So what do we see here? We see that along the y-axis, I've got two currents, that is IC and IL, and obviously they are of the opposite sign in a sense that you know, where you position them. When one is leading, one is lagging. The lagging one is positioned at minus 90 degrees, the leading one is positioned at 90 degrees. Effectively, it means that you can subtract the currents from each other. And in this instance, the IC, the current through the capacitor, is larger than the current through the inductor. So you can have what would refer as the resultant current, which is simply IC minus IL. So we can see that the resultant current between the capacitor and the inductor would be capacitive itself. The current through the resistor is unaffected because it is at 0 degrees with the voltage of the circuit, so it's not impacted by any of the phase shifts. So obviously then we can see that the resultant current, that is the supply current, would be a leading current somewhere in the first quadrant there. So the capacitor and inductor branch currents are antiphase, hence the resultant of IC and IL is IC minus IL. I've explained that, and it's 1.02 leading by 90 degrees. There it is. So this current, no longer this one, this is IC. This is the resultant current of 1.02. It's leading by 90 degrees. So we can then find what the total current is by simply saying I squared, which is the total current, is equals to I squared R, that is the current through the resistor, squared plus the resultant current, which we have just calculated, squared. And if we then substitute that into this equation, we know what's IR, we know what's IC minus IL, we have just calculated it. We find that the total current, the magnitude of the total current really, it's 2.24 amps. And we can calculate what the phasor angle is in the leading part. We know what IR is, we know what the total current is. We can use the cosine function, and then we can find what this angle is, the leading angle. So we know that. Since IC is greater than IL, the supply current leads the supply voltage by that angle there. So the angle that you would have found here, it's the angle with which your resultant current now, and when I'm saying resultant current here, I'm speaking about the total current in the circuit that comes from the supply voltage, would be leading that voltage by that particular angle which you would have found here. Right. Okay. So we want to look in some peculiar currents, not the straightforward currents that you have seen when you are working with either a resistor in parallel with an inductor or a resistor in parallel with a capacitor. So maybe the question one might ask is, what happens when you have got impedances connected in parallel, not just a resistor, but you have got a resistor in series with the inductor connected in parallel with the resistor in series with the capacitor. So you need to understand that. You need to understand that now you are working with not just components, a resistor, capacitor, inductor connected in parallel. We are working at combinations connected in parallel. So what we see is that, well, we know for starters that the voltages will remain the same. So the voltages it's not impacted, because a parallel connection essentially means that the voltage remains the same. What we would have, however, is that the currents, if, for an example, I have got a resistor connected in series with an inductor, a resistor connected in series with an inductor, and that combination connected in parallel with a resistor in series with a capacitor. The current that will flow through the RL combination, so the resistor and inductor combination, the current that will flow there will be a lagging current by a certain angle phi. And the current that will flow through the RC will be a certain current leading the voltage by a certain angle theta, for an example. So it is important now to know that it's no longer that way, like this in the current in your inductor, it's out of phase by 90 degrees. No. When you've got an impedance, it's out of phase by a certain angle other than 90 degrees. So it's important to know how you're going to deal with that. So if you have got two or more components that are connected in parallel, what you need to do is that you need to decompose that current, that total current, into its components. That is your cosine component and your sine component. So if, for an example, I've got a lagging current I, this would be, for an example, if I've got an RL circuit, I can have I cosine of theta, which is in phase with the voltage and is referred to as the active or power component. So that I cosine of theta is what we call the active or the power component. And I also have got I sine of theta, like so, which we call the quadrature or the reactive component. So this will be for the RL circuit, and this will be for the RC circuit. And the same is true. So this will be the active component, and this will be the reactive component. So obviously, if you look at them the way they are, you can see that I, this current here, I, it's simply I cosine of phi squared plus I sine phi squared. And you know that cosine of phi squared plus the sine of phi squared would give you simply 1. So that would all work out essentially to I squared. Now let's look at an example. A parallel network consists of branches A, B, and C. If A is 10 angle minus 60 degrees amperes, B is 5 angle minus 30 degrees amperes, and IC is 10 angle 90 degrees. All phase angles being relative to the supply voltage in this instance, meaning the supply voltage is our reference, determine the total supply current. So there you have it. So now you must be able to see here that you don't have R or X or what have you. You've got just a combination. So this will be Z, ZA, ZB, ZC, and so on and so forth. And they result with these currents. Now you can draw these currents in your phasor. There's your voltage, there's your IC, there's your IB, there's your IA, and this would effectively be your total current there. So I can take this IB, add it there. I can take this IC, add it there, and of course from the beginning all the way to the end, it should be able to give me what the total current is. So that's if you want to do the graphical summation of this phasor currents. So what you'd want to do is to find what the total cosine component of the total current is, and it will be the sum of all the cosine components of all the currents in the branches. So the cosine component of current A, the cosine component of current B, the cosine component of current C added together, they will give you the cosine component of the total current. And if you substitute that, with this information, you'd find that this The cosine component of the total current is 9.33 amps. You do the same thing with the sine component or the reactive component, where you add the reactive components of all the individual currents in the various branches. And when you substitute with the relevant information, IA, theta A, and so on and so forth, you'd be able to get that current to be minus 1.16. Of course, the minus there simply telling you the direction where it is. And in our case, it's going to be in the negative y-axis. It's a quadrature, so negative y-axis. So the negative sign indicates that the reactive current component is lagging. That's correct. So the overall power factor will also be lagging. We will deal with power factor when we move to the next chapter, where we deal with power in AC circuit. We will dwell a little bit more on what a power factor is. So what is the total current really that comes out of all this different currents connected in parallel flowing in these components? Is that we have found what the cosine component is and what the sine component is. So our total current is simply the square root of I cosine of theta squared plus I sine of phi squared, that's angle phi. And then it gives us the total current of 9.4 amps. The total current of 9.4 amps. Of course, we can find what the angle phi is if we use the arctan function, of course, using the sine component of the total current and the cosine component of the total current. So we see that the angle is that of 7.1 degrees. So the total current really here would be I being 9.4, lagging at 7.1 degrees. Right, another example, a coil of resistance 50 ohms and inductance of 0.318 is connected in parallel with a circuit comprising a 75 ohm resistance that is with a 159 microfarad capacitor. The resulting circuit is connected to a 230 volts 50 hertz AC supply. Calculate the supply current, be the circuit impedance, resistance, and reactance. So there you have it, a circuit that looks like this. The first thing, of course, that you want to do here is to calculate what your XL is, what your XC is, and then you will recognize that here I've got an impedance, here I also got another impedance there. So that's what you do. You find XL, it's 2 pi FL, it gives you 100 ohms after substituting with the relevant values here, where frequency is 50 hertz and the inductance is 0.318 Henry. So we find what Z1 is. It's simply R1 squared plus XL squared and the square root thereof. The square root thereof, you find 112 ohms. So you find what I1 is V over Z1 is 2.05 ohms. What is the angle? The shift of the angle? It's if we use the cosine function, then it will be R1 divided by Z1, and we find that it will be lagging by 63.5 degrees. So I1, that's the current that flows in this branch here, it's simply going to be 2.05 angle minus 63.5 degrees. So when we go to the branch where you have got a resistor connected in series with the capacitor, we find what XC first is, 1 over 2 pi FC. We substitute in this equation by the relevant information, the frequency, the capacitor, we find that XC to be 20 degrees. And of course, we can find Z2 to be the square root of R2 squared plus XC squared, and it gives us 77.7 ohms. From that, we can find what the current I2 that flows in that branch is, and it's simply V over Z2. And therefore, the voltage is 230. Z2, we have calculated it to be 77.7. Substituted there, we to find the total current to be 2.96. What is the angle, phase angle between the voltage and the current in that branch? if we use the arctan function, we need to know at least the components of the impedance there, rather, that is XC and R2, and we do know that. And therefore we can find what the total equation is. Yeah, so here I think what this should have been XCR2. So the textbook, I think they did a mistake here because they used Z2. So the textbook used Z2 instead of R, and R is 75. So take that mistake into cognizance when you are starting this problem. And we find the angle to be 50 degrees leading. How do we know it's leading? Is because we know this is a combination of a resistor and a capacitor, so the current I will be leading. Right, so that's the current of in branch 1, and the current in branch 2, it's given as 2.96 at angle 15 degrees. It's a leading current. So phasor sum, we want to know the total. The point is to find what the total current is. So the total current would be that we would need to find the cosine component of the total current, and that cosine component of the total current is the sum of the cosine components of I1 and I2. So you need to calculate what the cosine component of I1 is added to the cosine component of I2. And once you add them together, you would have the cosine component of the total resistance. Now, the same is true for the sine component, or rather what we refer to as the reactive component, and this language of active and reactive will become more pronounced when you start dealing with powers. So for the total current, so the sine component of the total current will be the sum of the sine components of the various currents, in this instance current I1 and I2. So for an example, I sine of phi would be I1 sine phi of 1. So this is in our case the RL circuit, the current from the RL circuit, the current from the RC circuit. If you substitute all the relevant information, I1, phi 1, I2, phi 2, you find that the current is minus 1.07. And again, this minus 1 simply tells you the location of the current. It tells you where the current is relative to, for instance, your voltage in this instance. So what's the total current I? We have calculated what the cosine component is 3.77. The sine component is minus 1.07. And if you square that, take the square root of all of that, you find the current to be 3.9. So now we want to calculate, what was the question? The second question, the circuit impedance, resistance, and reactance. Yes. So what's the total impedance of the circuit? The total impedance would be the total voltage over the total current. We have just calculated what the total current is. We know what the total voltage is. Then we can find what the total impedance is by simply saying the total voltage V over the total current. Yes, the total current is 3.92, if you like. And we find it to be 58.7. So the resistor and the inductance, or rather the reactance, if let's put it the reactance, because this is really a composite of everything that's in the circuit. What's the total aggregate resistance of the circuit? What's the total aggregate reactance of the circuit? So you'd use this impedance, the total impedance of the circuit, cosine of phi. So this is just the normal phase shift that you would have gotten between the voltage and the total current, the voltage and the total current, and therefore it will give you 56 ohms, and the total reactance of the circuit would give you 16 ohms. Since I sine of theta is negative, the reactance must be inductive. Thus, the circuit is equivalent to a 56 resistor in series with a 16 ohm inductive reactance. Right, power in AC system. This is chapter 12. Today we have done chapter 11. We have started and finished chapter 11. Next time when we meet, we will discuss power in AC system, which is the subject of chapter 12 in your textbook. Thank you very much, good people. I'll meet you again tomorrow. Thank you.